Hello and welcome back to episode 3 of Maths. This is simple integrals, and I'll go through what I mean by simple as we go through the video. This is the integral sign. Nope. Ready, why would you do this? So a few things you'll need to know, and that are derivatives, and that an integral is actually just another word for an antiderivative. So a derivative, say we have our function is z plus or z plus minus mx to the power of n divided by n. That should say divided by a actually, because it doesn't have to be n. A derivative of fx, or the function, would be the derivative of that, which would basically be take the power, multiply it by the equation, and then take that same power that you just had and do minus 1. An integral is an antiderivative, so if you can probably guess what that is, then you're going to do the opposite. So say we have this equation, we could say divided by a, but too much work to do. It'd get very complicated with all the letters and symbols, and we're going to do an integral of that, of the function, and we're going to put dx because it means little change to x, but I'll explain that later. So then we do the integral of the equation we've written down now, so that we know what fx or the function is, and then we just take the power, do plus 1, and then divide by that new power, so we get this. Now here it says, if we do an integral and then we do a derivative, or the other way around, if we do a derivative and then an integral, doesn't really matter, they do cancel each other out. You can also do it the other way around, where in this one I've done the integral and then the derivative. You can do it the derivative and then the integral. I think that would be much easier right now, because then that would mean 1 times x to the power of 0. So then we just get left with x to the power of 0, and then do an integral, then we just divide by 1 and do that 0 plus 1. Yeah, that'd be much easier. But essentially, we do the integral, so we have x is equal to x to the power of 1. Any number to the power of 1 is itself, any number to the power of 0 is 1. There we go. And we do plus 1, so now we get x squared divided by 2, and then to do a derivative of that we take the power, multiply it, these two cancel out, and then we just do 2 minus 1, which is x to the power of 1, which, as I said here, just equals x, which initially equals our function. Say we have a graph, then f function equals x, that will just be like y equals x. I think it looks like that. Seeing as I haven't actually labelled it, it would. And also we can put numbers in place of x. So say the function, say the function was equal x. Then if we did function 2, then y equals 2 because y equals x. Here we have 4x minus 2. So y equals 4x minus 2, do function 2, and then we get 4 times 2 minus 2, 4 times 2 is 8, minus 2 is 6. So here are some applications of the real world. So we have this graph, and we want to find the area here, and we know the function. I know this function will be something like sine, and you might be thinking, well, how do we do an antiderivative of sine? Sine is a function. Now, of course, you can get opposite for sine, but in this, it's weird stuff like negative cosine, and it's just too much for me to put into a video. You'd have to read about it and research it yourself. I'm very sorry about that. And it's been used to prove certain things. I didn't write that, I just got this picture off the internet. But that looks much neater than anything I could do, though. And it can be done in physics. It can be done as university work. It's very useful. It's more useful than you can imagine. So here we go. Do you remember this graph? It was right here. So let's pretend that, I know that this is a sine, but I don't want to do it in the video, so let's just pretend that this was y equals 4x squared. So, say we wanted to find this area. Well, first of all, do our integral, and it's already written here what we have to do, so all we have to do is just substitute that for 4x squared. So we do from a to b. It doesn't really matter if I put it above or next to it like this. And it does work in the same way as summation, so from A to B, but you don't exactly do it in the same way. I'll explain as I go through. So 4x squared dx, this equals, and if you remember how to do an integral, so 4 times, so squared. So here we go. We've got 0, this is 0, so this cancel out, and take it out here, take it out here. It's not needed because it's 0, it doesn't affect the equation. And m is 4, n is 2. So then this becomes 4 and 2 still, and then this becomes 4x 3 divided by 3. So then that would just be, no. So now we don't draw the integral sign, we draw the integrate sign. So it'd be 4x cubed divided by 3. But also using certain rules, you could take out this 4 and put it over here. Yeah, you could just take it out, because then we draw this huge pipe sign, A, B, and all this means is put b into the equation of x, so 4 times b cubed divided by 3, and then subtract a into the equation, so 4a cubed divided by 3. And using algebra that we learned in the first lesson, we can group the 3's together, group the 4 together. I'm going to need a bigger divide. B to the power of 3 minus a to the power of 3. And there is a rule that we can use. If I just go back to what I said about taking the 4 out, yeah, I'll just use this razor. Bear with me for a second. Just going to have to erase all this out. You can take the 4 out and put it over here. And then, because as you saw when we grouped it as 4b cubed minus a cubed divided by 3, if you remember about how we multiply with a swap around with fractions, we can just keep this 4 over here, get rid of it here. We could keep the 4 up there, move the b cubed minus a cubed over here, or wherever. So we can take out things that are being multiplied in there, as long as they're being multiplied by absolutely everything, which will have a term of x. And if something doesn't have a term of x, say it's just plus, don't worry, I'll get to it later. So then we'll just do x, that was a weird x, that's a 3. What am I doing? So then I just do x cubed divided by 3 with the pipe symbol from a to b. I put in the values, b cubed, oh, and it's still 4 times, b cubed minus a cubed divided by 3, as we did the factorization earlier, times 4. And there we go. So here's the rule. So let's say we have this, c can equal 1, and as we saw in this equation where it was 4x squared, c would equal 1, z would equal, or z would equal 0, n was 4, x is x, n is 2. That's how we get 4x squared. So let's put this in to the integral, then we integrate it, and this should be times c, but we'd put this in brackets, whoops, times c. And now, what do you notice different about here and here? Well, as you see down here, it says we don't have the plus minus z. And if you read it, I'll give you just a second. Wait a second, I don't think you can see it. Does this help? Maybe I need to make this smaller. Hopefully that should help. Maybe that should help. Either way, what it says, even if you can't read it, what it says is we don't have the z in there, because if we ignore all of this and everything and just leave it back to the 4x, say it was the 4x squared, and we said minus 6, then when we integrate that, let's just say that's our function, when we integrate that, then that becomes, I'm going to have to rub this out, sorry, 4x cubed minus 6 divided by 3, no, sorry, b cubed minus 4a cubed minus 6 divided by 3. But seeing as we put brackets around here, that means we're going to have to minus all of this against that. Now that's fine for doing factorization, because then we can keep the 4's together. B cubed minus a cubed divided by 3, that's all correct and fine. But then we get this minus and this minus. These two minuses come together and they make a positive. So then we're left with minus 6 and plus 6, which together cancel out and make 0. And even if we didn't, so even if they were positive to start off with, when we still integrate, we still do a subtraction, and that then makes this one a negative. So then we've got plus 6 minus 6. So we don't keep the z/z, whatever you want to call it, in there, because it just cancels itself out, or the integrate cancels it out. Now, I forgot to put dx here, but you're probably wondering, what does dx mean? So I'm going to use this as an example. So, a cone. We have a nice cone on a graph. What's the area of the base of a cone if it was 2D? That's pi r squared. Now pick any point between 0, 0 and your height along the x-axis and click. There we go. We've got this point. And then we go up and there we go. That's our radius. Woohoo! So then we've got pi r squared. I did that again. Around here. And here. We've got another pi r squared. Here, another pi r squared. But what's the distance? Well, seeing as there is no smallest number in the world, because you can keep on going, the distance between all of them would be 1 divided by infinity, which you would say is 0, but in this we're actually calling it a real number. Well, actually a whole number. But then that would just mean that it'd be 0. An infinite recurring amount of zeros with a 1 at the end. and this doesn't often happen in maths. But with this, that's what the dx means. So it means just a little minuscule, so minuscule you can't even see it change to x. That's what these graphs up here are showing. The infinitely small slices we should have. Now, of course, a computer can't simulate infinitely small because it just can't. It would reach a breaking point and crash. Or it would just never stop running the program if the computer was that good, and then crash. So that's what the dx part means. So it just means our infinitely. So we've got perhaps rectangles, you could call it, and that revolves around a pi r squared amount of times, but the length is the diameter, and the diameter is calculated from 2 times the radius, and the radius is calculated from the point of which you picked, but the width is 1 divided by infinity, whilst that becomes a member of all real numbers, and that looks like a B, whilst 1 divided by infinity is an element of real numbers. So, speaking on cones, let's use that. So now we're going to prove the volume of a cone in 2 ways, and that's what also will be covered. And this is getting to some very high level maths. Right now, the maths involved is very high, I'll just tell you that. So, first we're going to need to know what the function of this line is. We know that the beginning x point is going to be 0, 0, and the end will be the height. So, let's draw out our beautiful integral. We know the beginning is going to be 0 and the end is going to be height. The function, well, we go down by r, we go across by the height. So it's negative r divided by the height, x, and the y-intercept is here, which is r. Now it's the area of a circle. So now we've got all our infinitely small radii, and the area is pi times r squared. So this divided by h x plus r squared. We can do what we did earlier and take out pi. So now this equals pi times integral of a complex quadratic. But that's okay. Divided by h x plus r. I'm not sure if I covered quadratics. I think I did though. But at least you'll be able to go off and solve it. So now I'm going to have to try and solve this. So these two would come together. A negative number times itself would become positive, as we know from square rooting. So negative 4 squared, which is negative 4 times negative 4, is positive 16, always, which is how we get imaginary numbers. Watch the first video I did if you want to learn more about that. So then that's going to be r squared, if we take these two together, divided by h squared, x squared. Then these two is just going to be r squared divided by hx. Let's start writing this down somewhere. So that divided by h squared x squared plus. Oh no! It's negative. Nearly caught me out there. You see? And now we've got that part done. Then when we do this one and this one, it's going to be the exact same. So why did I do that? So now we can say negative 2 times, so that we don't have to do this again, of r squared divided by hx. And now all we have to do is r times r, which equals positive r squared. So let me just erase all this so that I have space to write, because I don't think I made another another slide to write this all on. So I'm going to have to rub this all out. But now we have our radius, and all we have to do is integrate this. So it would be pi times, and now we're just skipping to the integrate part rather than writing this all out inside an integral. Sorry. R squared divided by h squared x, wow, always do that today, x cubed 1/3. Now with this one it's normal x, which means x to the power of 1, and then that would be up to 2, and then divide it by 2, and here we get 2 divided by 2, so that cancels out. So what we're left with is negative r squared divided by hx squared, and here plus, and seeing as there is no x on this, that means it must be r squared times 1, and when we say times 1 we mean x to the power of 0, so it's going to be r squared x, and then we'll integrate from 0 to h. Now seeing as everywhere there's an x it's always being multiplied, then that means the entire thing is going to get multiplied by 0. At some point we can factorize all the x's out, so no point integrating with 0 and writing it all out. So all we have to do is find it in terms of h, and that's it. Cancel out and you're done. So that would be pi r squared divided by h squared times x now becomes h cubed. Now seeing as that can be taken up there, we've got h cubed divided by h squared. And I don't think I covered this in the video, but then that r squared, then h cubed divided by h squared. All you have to do is the h subtract 3 and 2, which becomes 1, and we just know that just leaves us with h. So we can get rid of all this, and we're just left with pi r squared h 1/3 negative r squared divided by h squared as we did before. Just get rid of this divided by h. So now we're left with negative r squared h, and here again positive r squared h, and these two cancel out. Oh, I forgot to write 1/3 in here. So then we're just left with 1/3 pi r squared h, and that is the area of any cone. Now let's try a less complex way, where we don't have to do so much of the quadratic. Let's just say the cone was this way around. So here, the base was over here. Here, the base is over here. Your height can still be here, and 0, 0 can still be there. Doesn't really change much, it's just in this one we were going negative r, positive h. In this one we're going positive r, positive h. So all we have to do is integral from 0 to h, I think I'm doing this correctly, pi times r divided by h. My gosh. Divided by h x, and we're just going to square this, and that shouldn't be too hard because that just looks exactly like when we had to do the quadratic with this times itself, and it's perfectly correct. It's going to get the exact same answer. But, so we can take out pi, and now we're just left with pi, sorry I'm writing it down here, pi times r squared divided by h squared x squared, integrate from from 0 to h. As I said before, no point putting 0, seeing as it's all going to get multiplied here. So you might as well just put h into the equation, then you're done. So pi, oh I forgot to put x cubed 1/3, pi r squared divided by h squared h cubed. Looks very familiar to back here. We had h squared and h cubed, so these just cancel out. And that's a freakish h, so is that r. So I'll just rewrite them, r squared h squared, and no more factorization has to be done. There we go. That was a really simple way of getting pi r squared h 1/3, but this is just a proof to make sure that we did it correctly, and it works both ways. I could do a sphere, but I don't have enough time. So, like, subscribe, leave a comment, and I have no idea what I'm going to be doing for next video. Thank you, and this was some A-level work and degree level work.